Welcome, ladies and gentlemen, to my step 3 presentation. I'm Alireza Alizadeh, and this is CS Internship. I'm going to talk about all the technical details and all the technical material that we went through in this step, and we're going to skip over some because there was so much information in this step, and if we were to go through every bit of it in details, we're not going to have enough time. The first bit of information that you're presented to is functions in Python. Functions in Python are basically an encapsulation of your code. You define them using the def key and a name and a bunch of parameters. You can have your parameters named, or you can just have a parameter and mark it with an asterisk to capture all of your unnamed parameters, or mark it with two asterisks to capture all your keyed parameters. For example, if you have like key 1 equal to 2, for example, this is going to be captured by this one, and if you just have the number 2 by itself, it's going to be captured by this one. The idea is sometimes you need abstraction in your code. You need to reuse your code, and you don't want to retype every bit of code, and these are what functions are for. Some languages have something called a procedure. So a procedure. The difference between a procedure and a function is that a procedure doesn't return a value, doesn't have this. It's just a set of instructions. But Python technically doesn't have a procedure. Even if you don't have a return expression in your function, it's just going to return none in Python. So that's something that you might need to keep in mind while you're writing your functions. And if you need a procedure, just don't use your return statement. And that's going to simulate having a procedure for you in Python. And that's basically all the things that I'm going to say about functions. Functions have a lot more in them, and they can be experienced, and they can be used in a lot more depth with like decorators and generators and different kind of expressions and stuff like that. But this is just what we're gonna say is enough for now, and we're gonna move into our second subject, which is modules and scope. Modules are one of the best things and one of the best tools you have to keep your code clean. So it's not a scary subject, and it's not a scary thing to learn. It basically means keeping different parts of your code in different places. For example, if you have a robot and you're trying to code movement for it, you can have different kind of movement in different files, and you can import these to your main file when you're going to use them. And another example of this is, for example, if you're solving something like a transportation problem. So a transportation problem. You might need a UI to get the problem from your user and define your problem. And you might need a bunch of solvers like the northwest method or row minima method and different methods that we have for transportation problems. You're going to put this UI in another file called, for example, ui.py, and you're going to have your solvers in something like solvers.py. And in your main file, you're going to just import these and use them in your main file without cluttering it and keeping your main.py fairly clean. So that's the idea behind having modules. And the other idea is scope. The scope is pretty rudimentary, and in Python we don't really have hardly defined and set in stone scopes. You can use auto scope things by defining them and using special key variables like global. So for example, if I'm here and I need to use something that's, somewhere else, for example, in here, I just need to import it. Even though it's not in scope, I can bring it into scope. Or another example is in functions. So you have a function called foo, for example, and you have a variable x here equal to 0. But you also have a variable x, which is outside of your function. So this function, this x, the x that we have above, this one, is out of scope. But this one is. How can we sync those? You just need to make x global. So if you make it global x, then it's going to be the same x. So that's the idea of having scopes and how we are dealing with them day to day and line by line in our code. The thing is, you need to be careful with scopes in Python because indentation affects a scope in Python. So if you have a function like bar and you start your code here and you have another code here, this code is not going to be in scope for this one because it's not preceded by an indentation like the code previous. So be careful in Python. We don't have curly brackets and parentheses to make sure we are in scope. We just have to look at it and see if the indentations are correct to make sure our scope is correct and our program is doing the things that it needs and it has access to the things and variables and different functions that it needs in the right scope. Moving on from scopes and modules, we are gonna go through object-oriented programming, which is something that I touched on last time and in our last presentation for step 2. If you remember, we said that classes are the way we implement object-oriented programming in Python. So you have different classes. And I said that classes are basically an encapsulation of a bunch of data, which you have here, and a bunch of methods and functions, which you have here. All the things that I've said until now are just a review of what I said before. Now to talk about inheritance. Sometimes you have classes that have the same attributes and have the same methods. The idea is you shouldn't need to redefine all those methods and redefine all those data and clutter your memory. So you inherit them from a base class. So for example, cats and dogs are both animals. And they all have names and ages, like all animals. So these are inherited here. The name, for example, is inherited, so is the age. And all animals eat and sleep. So we're gonna inherit these functions instead of rewriting them. However, sometimes our animals do different things. For example, dogs bark and cats meow. Cats climb trees, dogs fetch. And you add to those methods and to the data sometimes, you can have extra stuff here too. You add to the attributes that you inherit and make it its own class. And this way your code stays cleaner, your data stays cleaner, and you have this logical relationship between your classes and how you store data, which helps you implement more complex things and more complex logic into your program. Moving on from Python, we're going to dive right into linear algebra and matrix decompositions. If you remember, in the last step, we talked about linear equations and a system of linear equations and how we can solve them. And there we talked about decompositions, that if you need an easier time solving a system of linear equations, sometimes you need to prepare your matrix and decompose it into multiple different matrices so you can solve it easier and with set algorithms. In this step, we're going to dive a bit deeper. We have four different types of decompositions. You have the LU decompositions, or it's sometimes in some colleges, if especially if you're in our country, is referred to as the Gaussian decomposition. Then you have the QR decomposition, which is very, interestingly named by the same letters. Then you have eigenvalue decompositions of a matrix, and you have the singular value decomposition, which is also referred to as the SVD decomposition. The idea is every single one of these decompositions has its place and has its use. It's not like we're gonna say, okay, these two last ones, and especially the SVD decomposition, are very powerful. I mean, let's just factor, eigenvalue decomposition and just talk about this SVD decomposition. This decomposition works on everything, like every matrix. Anything that you throw at it, this is gonna solve it for you. No problem. But the problem is it's very cost intensive, and it's gonna take a lot of time and a lot of resources to do this decompositions. And if your matrix is fit for example, a Gaussian elimination and for an LU decomposition, why not just use this one? Or if you can use QR, why not use a QR decomposition? So when to use these and where to use these is a great question, and it's a bit hard to answer, to be honest with you, because I remember having a 90-minute class with my professor, and all we talked about is where and when to use these, and we didn't really come up with a solution, to be honest with you. But here we come to one of the most beautiful pictures that you're gonna see in your life, and it's this one, the matrix world picture. So the idea is you have different types of matrices. If your matrix is just a normal one and doesn't have any fancy propositions, properties, you can use SVD or you can use CR. If it's in a square matrix, if it's singular, use LU. If it's invertible, QR. And you come down and down and down, and if it's normal, you can use your eigenvalue decomposition, and so on and so forth. And sometimes you can move matrices and move them to another place where you can use different kind of decompositions on them where you couldn't do before. The question becomes a bit of a doozy when you have a matrix that's here in the normal zone. So you can use all the decompositions for it. So which one do you use? Which one should you use? And the solution that we came up with, my professor, was, since they have such different costs and they need such different amount of resources between like an SVD decomposition and an LU decomposition, let's just start with the one that has the lowest requirements in terms of resources, not in terms of mathematical properties. So you just start from here, basically from the top, and go to the bottom, because if you have the resources and if you're not super tight on time and you can experiment a bit, if you can get away with a low cost method, why not? Just try it. It's not gonna hurt you. You don't need to sit and calculate every bit of memory and every bit of CPU used and measure them and think about, okay, how much do we gain, how much do we lose? Just start with the simplest one and move to the most complex one. If none of these work, the last one will. Good job, you did it. Your matrix is now decomposed and you can go on and solve your problem easier. So yeah, just that's my advice. I don't know how much it's gonna translate into production code, but that's what we did back in college, and just started with the simplest one, and if it didn't work, just up the difficulty a bit, and if nothing works, SVD always works. So that's all I'm gonna say about matrix decompositions, and it's always good to have these two pictures with you, just to know what can you use, how can you maybe sometimes transform it to use different type of decomposition and stuff like that. And moving on from this, we are going to talk about the last subject matter, which is vector calculus. I'm not going to talk about all the bits of it because it is a heavy subject and it is a time consuming subject. What I'm going to do is focus on the subject that I like most and I'm interested about, and that's backpropagation. Backpropagation is a lovely idea because sometimes you have a neural network and you give it an input here and it goes through all these layers. Like it goes from layer 1 to another layer to another layer to another layer, and in the end you have an output layer which outputs the whole machine's work, and you get sometimes an error. The idea is, how can we adjust our neural network that we have here with respect to this error? Well, for the error, the first couple of layers are not really hard to adjust for because they were in direct contact with output. So you have your error here. But how can we adjust our first layer with respect to this error and these many layers that we have in our way? Well, your solution is going to be using the chain rule. So chain rule and partial derivatives. So this is the partial derivative of f with respect to x. Remember that word respect. So we need to respect all these layers. So we need something that respects them. So you just partially derive from your error, which is just such a beautiful thing to do, and using this chain rule. And in respect to this layer, then in respect to this one, then in respect to this one. And you just go back until you meet your first layer, and you have all your adjustments for all your different layers with respect to the path that it was taken. So for example, you could do in respect to this, to this, to this, to this, and in the end to this one. So you respect all the layers you have, you respect your error that your output layer has given you, and you adjust all your weights without, leaving anyone out. And that's all I have to say for this presentation. Thank you for listening, and I'll see you in the next one. Bye-bye.